Okay, I guess to keep us on schedule, I'm going to kick off our next section. They asked me to talk about underwater robots, which will be fun and interesting. I did not get my start in underwater robots. In fact, I got into underwater robots because I came here to work with Red, and then he sent me to the desert, and the desert was hot during the day and very cold at night, and I slept in an RV, and I thought, I got to do something that takes me to warmer, nicer places than ground vehicles, and that's how I got into underwater robots. So I wanted to kind of hit on underwater robots because I think we are a much smaller area that's met with much less fame and success than ground vehicles and aerial vehicles. But I do think it is part of the long and rich legacy of field and outdoor robots, and a particularly good use case. So after I left CMU, I got into trying to use optical cameras in the underwater context. And so we started building camera systems to place on big outdoor vehicles that go pretty deep. And so sort of the core thing that we ended up building is these kind of camera systems where you bring all your own illumination, rated to a couple thousand meters, with the goal of doing the same things that everybody was doing on land, but doing them underwater. So the big sort of application was SLAM, and obviously a natural fit because you don't have any GPS. And so using all of your exteroceptive sensors to build a map seemed like a good idea. And we started building large-scale maps. This is off the western continental shelf of the United States, down at about 1,000 meters, and obviously a very inhospitable environment. This is work done in the context of NASA with the goal of trying to build proxies for space exploration, because obviously very limited comms, just acoustics, a very low bandwidth, high latency, and then obviously a pretty inhospitable environment. These are bacterial mats and mounds that get created by upwellings of hot water. And so we started doing this. We kept doing it in a bunch of different places. And so I got to travel the world trying to build these kind of maps and then hand them to both marine biologists or oceanographers or people that are generally interested in trying to understand the deep oceans. And I think it's been like a really nice and natural fit to the field robotics ethos, because you end up having to do a lot of scrambling in the field. You're out on a boat with, again, very limited comms, very Spartan conditions. And so I just kind of traded from living in an RV to living in a very tiny bunk aboard a big research vessel. And ultimately, I'm not sure that was much of an upgrade. We kept building underwater vision systems. So this is on a vehicle that the University of Rhode Island operates. And so in addition to doing marine biology work, we got really interested in cultural heritage preservation. And so we did a lot of shipwreck work. So this is a shipwreck off the southern coast of Turkey, again, down about 650 meters, so well beyond where divers can sort of hang out for a long period of time. And we're building both visual maps, but also 3D reconstructions, again, simultaneously, in this case, using stereo cameras. But you can see the kind of fidelity you're able to gather underwater. If you bring your own illumination, you do a lot of things to try to clear the images up. You can see little tiny starfish. These are amphoras that used to carry wine or grain in the ancient world. And in fact, after we took all this mapping data, we were also able to, they sent down and gathered DNA samples of the crops and grape strains that were being used back then. So again, there's a lot of things you can do. Put it together in sort of nicer and more fun environments that I got to go to. We did a bunch of work in Southern Europe, and so I got to go to the southern bit of Greece on the Peloponnese. We got to do diving. This is one of the robots we deployed there. We also built and deployed robots pushed by divers themselves, but again, with the same kind of technology that we were seeing on our field robotics. So this is LED illumination, stereo cameras facing down, and then when you're on the surface, obviously GPS. Using that, we're able to cover a really extensive area of a submerged city that hadn't been mapped since 1968 on the southern coast of Greece. And they had done this extensive mapping with marine archaeologists back then. And what they did is actually take survey equipment, put it in the water, and then survey from land. And it took them about 2 weeks to build that pretty coarse map you see of all the roads, streets, and buildings that are in the submerged city. And then in 2 days, we were able to go, and the red is with what we did with human push divers, and then the blue we knocked out in about 4.5 hours with an AUV. But we cover this extremely large area at very high resolutions, over 200,000 stereo pairs, and you can see that you get this really fine detail where you can see individual rocks, stones, pebbles, and we're able to map the streets, the roads, the former buildings, all of that, and put that together into a map. Probably the last thing I'll hit on here is we did a bunch of work trying to understand the impacts of climate change on marine ecosystems. So this is several reefs off the western coast of Australia, and what we did is we went over multiple years, and this is still an ongoing project that's funded by the Australian government, so they continue to do robotic mapping and survey work even now, almost a decade later. But we would go and over subsequent years, look at the exact same places, try to figure out how to localize down to the level of fidelity necessary to compare. And you can see very sadly that over these kind of couple of years span, you can see the corals bleaching. So on the left, you can see the original chunk of coral we're looking at, and then you can see on the right that parts of it have turned completely white. We were able to track and understand over sort of multiple years the changes in both water temperature, salinity, acidity, and then map that to different bleaching events that are occurring around the globe. So anyways, I guess when you're all out with your ground and your aerial vehicles being incredibly successful, doing really well, remember us poor, sad, underwater field roboticists who don't have any of the hype, VC funding, glitz, or public media exposure, but there's lots of fun things that we're doing underwater, and thanks. I'm going to bring up Michael, who may change all that. He is working on making lots of money out of underwater robots in a way that we have been unable to today.
Okay, we'll see about that one. That's at least the hope. Right, thank you. Yeah, so I'm Michael Kaess. My research is in localization and mapping, navigation, autonomy. I thought since underwater is a bit out of the ordinary, I wanted to start here just giving a quick intro. So most of the planet is actually water, most of the surface of the planet. And while we have mapped land, we have not really mapped most of the underwater environment, right? So only about less than 25% as of last year of underwater was mapped. So there's a big challenge out there, and it's because it's really difficult. So what makes underwater difficult, and especially robotics, requires facilities, right? Even to do any testing, a test tank, for example, here, as in the high bay, that's 130 tons of water. And it's a very small environment to do anything in, right? It's not much space in the 7-meter diameter. Salt water, that's a big challenge, right? The materials that you have to use makes everything very expensive, so it doesn't corrode. And then the big challenge is communication, and the radio waves don't propagate, so everything is acoustic. If you still remember acoustic modems, for example, from internet access 20, 30 years ago, that's basically the state for underwater robotics. There are lots of different platforms out there. So autonomous surface vehicles are actually, at the moment, very popular, and that's for reasons of conflicts in this world. For underwater research, it's more the conventional platforms. These torpedo-shaped vehicles are pretty large, typically, that are being used, and that is pretty well developed by now in terms of autonomy. Really, over the last 10 years, since the Malaysian plane went missing, for example, at that point, it became clear that some more capabilities were needed to do mapping. What we really focus on is the bottom left here, hovering vehicles. So vehicles that can be used, that are slower, but they can be used in 3D environments. So if you think of infrastructure near a dam, bridge piling, near ships, that's really the way to go. And that's a bit similar to drones in air, except that there's lots of challenges, right? That you have no visibility, for example. I'll come back to that. So question is, how do you inspect the ship? Typical state of the art is you pull the ship out of the water into dry dock. That's terribly expensive. The ship is out of service for a while. Could you do this in water as the ship is operating even, or at least sitting in harbor being unloaded? And so this is work that was sponsored by Navy over many years. The challenges here are low visibility. So unlike where Matt was operating, where you have great visibility and get images, if you operate in Baltimore Harbor, you cannot see the hands in front of your eyes. You have basically zero visibility. And no radio signals, that means there's no GPS. And that means there's a localization problem. So it's a typical simultaneous localization and mapping problem. You have to build a map of the environment, and you have to use that to localize yourself. So the bottom right here, let me see if this is playing, if this did play. No. In the bottom right, this was supposed to be a video, you could see a 3D model generated just from sonar data, and the propeller of that ship is almost 7-meter diameter. So that's the size of our water tank. So these structures are really large that we deal with. This work really has to be done in the field, right? The tank is just to do preparation. So we've been out in the field on many different ships, some of them often like the Curtis, about 10 times out there in San Diego. There the visibility is a bit better at least. Very large structures like the hospital ship, that's a 1,000-bed hospital ship at the bottom right, almost 900 feet long. And the best opportunity here was actually an aircraft carrier, an old aircraft carrier, bottom left, over 1,000 feet. So if you're out in the field, you're not operating from the ship, it's way too big, right, to launch a vehicle from there. You're actually on a small boat doing the experiment. So in the circled area down there, oops, here we go. In the circled area, right, you can see where we actually were, and then pretty cramped quarters and everything moving, and no bathrooms. This is kind of interesting. But really, the structures here are amazing, right? The size of these, you really only appreciate when you're there and get to see this. So we fully automated this, and let me see, hopefully this is working. Should be playing automatically. Right, so this was supposed to be embedded. All right, so we have the vehicle autonomously covering ships, so ensuring full coverage. This was actually looking for explosives on ships, so it was important that you can find everything. We have cameras, we have sonar, and we can automatically plan a path along here as the vehicle is going. And let me just move on. There's a lot of interesting research behind. So using sonar instead of images, there's a lot of equivalence with vision. So we actually developed a line of research we call acoustic structure for motion. So doing 3D reconstruction from imaging sonar images. The geometry is quite different, but similar methods can be developed to do this. And this is really useful for localizing the vehicle and getting some sparse feature points in the process. But then if you actually want to do dense 3D reconstruction, that becomes quite tricky. And so we have shown that this is closely related to 3D reconstruction by looking around the corner. So doing non-line of sight imaging with laser is actually pretty much the same physics. And some of these methods could be applied. So very recently, getting into neural rendering methods, getting more into learning-based methods. You can actually do fairly decent reconstructions and even join different sensors. In this case, an imaging sonar on a camera, but we're working on other things for cross-modality. So you have multiple vehicles with side-scan sonar, with synthetic aperture sonar, or with imaging sonar that have to be able to collaborate. So it's a really interesting space to work in. So it's not easy to do experiments. In terms of future, this is very focused on my work here on inspection. I think autonomous infrastructure inspection is now doable. These techniques have matured enough. And so we started a company called autonomy. So the goal is to get people out of harm's way as these commercial divers, the work is actually really hard that they do, and it's really dangerous. So they got a lot of them get injured. We talked to many of them. Quite a challenging environment. Yes. So that's my view. Others do underwater robotics in near coral reefs. We've been working in Baltimore Harbor and other places, but I think the technologies behind that could be really useful, and that's what we're working on. Thanks.
Hello, thank you for having me, Matt Travers. I'm going to completely trash underwater robots. All right. So I'll talk about heterogeneous teaming under. So I'll start on a high point. So this was work that I did with Howie. So this is the only underwater robot I've ever actually worked on. So there's a little bit of truth here. So this was mostly just mechanical design, a little bit of path planning. It wasn't sort of a full autonomy package. However, we would like to start to put a full autonomy package on these robots. So this is the underwater snake robot. I think there was an IEEE. This got some decent press when the original videos came out. Very, mechanism E. It's a combination of internal articulated joints. The heavy actuators, if anybody knows, one of Howie's startups is Heavy Robotics. They make these servos. They do an underwater version. So there's a couple heavy servos in the center of this, and then conventional thrusters. So the vision, though. I don't know. So I think people or whoever was organizing saw that I worked on underground robots and was like, close enough to underwater. So for the primarily what I'll talk about is underground robots, and I just have a lot more to say there. So my life underground actually started around 2018 in the DARPA Subterranean Challenge, where I was working with Sebastian. We were the co-PIs for the Carnegie Mellon Oregon State team. And for anyone who's not familiar with DARPA Sub-T, it was to rapidly gain situational awareness underground, and it was in these different sort of target, locations. So a little bit of overlap underground, we face similar types of problems. Navigation is hard, sensing is hard, there's no comms, there's no prior map. It's all complete odometry. Sit the robots down, tell them to go. And the objective for this challenge was to go and locate artifacts underground in the littlest amount of time as possible. In order to do this, you needed to be able to obviously build maps. So you had to do full SLAM, then the perception, localize the artifacts within the map that you were building, and then accurately report those to DARPA in the least amount of time as possible. There was no specification on how you were going to go out and accomplish that goal. So this is actually video from the final. This was a DARPA-style competition. And it was a combination of those three different domains that I showed you. So it was urban, cave, and tunnel. So we actually had a team, I'll show in a slide or two here. We had a team that was a combination. It was a heterogeneous team. It was actually driving robots, walking robots, and flying robots. I believe at last count, I think during the finals, we actually had 7, maybe 9 robots. It was drones everywhere. It was ground robots. It was walking robots. There were stairs. It was sort of everything and all of the above. We did not win. I'll leave it at that. But yeah, it was a very, very good, learning experience for all. And I'll show, actually, this was actually what you're looking at here. So the DARPA people for the final competition had like Hollywood set designers effectively come in. This was in a mine in Kentucky, the Mega Cavern, a hell of a place. But they actually built effectively this set so that it would have those three. So it would have the urban, the tunnels, and the caves all in one place. It was actually pretty amazing. Interesting thing that happened here is we had never had that many robots all in the same comms network. So we had always been deployed underground, but in real caves so that there was limited comms. So you had sub-networks on your main network. On this, because all the walls were fabricated, the comms, we had full comms. So everybody was a fully connected graph, and it spoofed the comms network, and we couldn't get any information. So basically, the night before this was happening, we were up to like 4 a.m. trying to solve the communications problem, because it was the first time. You know, details matter, trust me. But anyway, so this is the infamous when our vehicle drove off a cliff. This is a pretty good robot. Oh, you can actually see it. Yeah, I guess we cut it out. That's a famous, the robot, the DARPA humanoid, whatever that I forget. But the blooper video from the last DARPA. This is our blooper video. Is the robot driving off a cliff. All right, so this was the final map. These are all the different UGVs. It was actually pretty remarkable in that final competition how much of the actual terrain we were able to map, artifacts located, that we did have our problems. In terms of very positive, demonstrable outcomes from this, there's a lot of people involved with this over the years. So about 36 active faculty and staff, some, familiar names up there. From many DARPA projects, a large number of graduate and undergraduate students, and this was sort of the highlight reel, so to speak, I think, for me and Bashi. And you can sort of actually see as the project progresses, our faces become longer and longer. So it was about 90 people total involved. It was at the time biggest by far project that I had been involved in, so it was, overall a very, very positive experience. On the technical side, this sort of charts, we built everything from the ground up. I don't think I'd ever do that again. But we, from the, I could tell you who welded the frames of each of these robots down to built the payloads. We built everything. The drones were custom. You can see the drone there sitting on the back of the ground robot in the videos if I'd let them play longer. We actually had the drones mounted on the back of 2 of the ground vehicles. The drones would automatically take off of the back of the ground vehicles. It was pretty cool. There was this sound, there was a latch, and the latch would, before the drone would take off, the latch would go kunk kunk. It was like the most satisfying sound that you could hear. So it was pretty cool. In terms of, again, sort of just tech development, you can actually see the evolution. So it's chronological, so starting in the back and moving forward. R1, R2, R3. You can actually see the payloads, this red payload. We like that one. We painted it red or anodized it red because people thought it looked like Iron Man's head. And then in moving forward, I have this acronym up here, USASOC. So sort of the outcome of this project, direct outcome for us, was another follow-on project where we started working with these good folks at USASOC. We had done really, really well in sub-T. They sort of had noticed. And in fact, that project still persists and is ongoing to today. So the payload, in terms of direct tech transfer, I guess, was the payloads exactly. So similar concept to, sure, a lot of people here in the room is this idea of modular autonomy, autonomy in a box. I put my modular payload on any one of these platforms. And above a certain level of abstraction, my autonomous system is modular. It's shareable. I can put it on a drone. I can put it on a walking robot. I can put it on a flying robot, or excuse me, a ground robot. Whatever. The sort of quantum leaps, I guess, from the Iron Man's head payload on R3 here to the MAP v3, the USASOC payload. We had 2 computers. We had a Nook and a Xavier in the prior generation. We got everything down. This is a lot of Bashi's work. Got everything down to a single GPU. All the cameras, the LiDAR, the IMU, everything is time synced off of just that one GPU. Got it into this small, nice looking box. LEDs, everything there. And yeah, the military folks were very, very happy with that. So that leads us sort of into the post-sub-T world. Here's just a look. Nice. When you get a graduate student that likes making videos, oh, it's so sweet. So this is just sort of a promo video that we had put together for this payload. This is just showing some of the features and the various things. So thermal in there, LiDAR, LEDs, and again, everything time synced. We made it, it admits comms, it'll do full SLAM, again, so it is a full autonomy in a box very similar to some of the stuff coming out of near Earth. That was the box. All right. So we took that box, and that the work with USASOC, this is just featuring, shows some of the features there. So this was heterogeneous. They wanted to be more fast moving, and sub-T, it was really just go out and explore. The USASOC folks are very interested in getting cameras and other sensors down tunnels underground as fast as possible. So ISR as primary goals. And we took a lot of the ideas and a lot of the autonomy, like the backbone from sub-T, and we really sort of went to task on making that truly heterogeneous. We started to add things like the ability to drive in convoy, to have more explicit collaboration between the robots, have done some really interesting things with, so underground is there's no communication, there's no prior communication, there's no maps, so you have to build everything. So in addition to building the map, if you want to be able to talk to your robot that's down range, underground, you need to drop comms repeaters. So in this project, the multi-robot, and you can see some of the robots driving together in a convoy. The idea is you want to be able to just drive that front robot from a user's perspective, and then have the trailing vehicles peel off and act as breadcrumbs. They become your comms repeaters, and then from the perspective of your operator, you can just operate that distal robot downrange as if it was sitting right next to you. This too, so that's a Spot robot, Boston Dynamics robot. So we've automated, the robot comes, you can climb stairs. It's actually a very amazing robot if you haven't worked with it. But in terms of autonomy, it's a good platform. So we've built autonomy on the top of that robot, and again, the same stack, a lot of what we're using to control the ground robots is what we're using to control the spots to a certain extent, what have you. All through that payload, this is some of Bashji's work, doing multi-floor mapping, and yeah, some amazing things coming out of this program. This is still ongoing. I actually have a demo we're preparing for next week. Yeah. So in terms of the modular autonomy, this is just, at one point we're working with the spots, and then the USASOC folks, the Army folks, decided they didn't like the spots. So they were like, all right, we're going to go to the Ghost Vision 360, V360. So they're like, all right, we're going to test your modular autonomy concept. So indeed, we were able to put this box on top of an entirely brand new robot. It admits navstat commands, so it takes velocity commands. And basically within a day or a couple days, we were able to start controlling new robot, never worked with it before, able to start accessing some of its features via our autonomy system. So really, again, taking the system and displaying hopefully some of its worth. And I can actually keep this pretty short. So with this, we've been, again, developing sort of the baseline system, getting the comms, getting the navigation, whatever. We're always, for this, metrics for success is always going to be pushing speed. So again, these are meant to be operational. These are recent-ish results. This was an abandoned VA hospital off of Washington Boulevard. If no one's ever been there, well, you're not going to go there now. It's been condemned. But this was like the robot playground for a couple years, and it was pretty sweet. You didn't know how good you had it. And so, yeah, you were looking, we affectionately referred to it as Hawkins Laboratory, if anyone's seen the first season of Stranger Things. But this was some of the high-speed navigation. Again, I was trying to push the limit on how fast we can drive these vehicles. Sorry, for context, the hospital at night is, because the buildings are connected via long tunnels, is actually a pretty good simulation for being underground. So high speed in confined spaces is probably the best way to think about this. And this work, in terms of just me and personal timeline, then really fed into, looking at you, Mo, and a couple other folks, to a recent DARPA-ish program that was the DARPA Racer program. So this was full-size ATVs, buggies as they're referred to here in Western PA, driving quickly through the desert, fully autonomous. So visiting, one of my favorite statements is the reason we call it research and not search. So back to the desert, back to full-size vehicles. And this, again, was really starting to push the envelope on speed and, some interesting things here as as you start to go faster, you start to reach like the physical limits of what you can do in terms of processing speed, what you can do in terms of processing perception data, and you really need to start thinking about not just taking the data, but now starting to infer things. So being able to actually reason about uncertainty and really making a system that's much more sophisticated than there's an obstacle in front of me and I need to drive around it. You really need a system that can start reasoning on partial information, which is where I think a lot of my work and my career will be going for years to come. With that, thank you very much. Appreciate it.